Okay, so we are discussing the properties of Laplace transform. So in this lecture, let us discuss division by t. That is, you have a signal x of t, and then if you divide by t, what is the Laplace transform? And then we will talk about initial value theorem and final value theorem. Okay, so if you recall from the last couple of lectures, we have seen some duality in the relations between the Laplace transform and the time functions. For example, if you differentiate the signal in the time domain, then its Fourier transform will be s times x of s minus x of 0 minus. Similarly, if you, so here in the frequency domain there is a multiplication of s. If you multiply in the time domain t times x of t, then its Laplace transform will be minus d times x of s divided by ds. Similarly, if you integrate in the time domain x of tau d tau and integrate 0 to t, then its Laplace transform will be x of s divided by s plus x of 0 minus, and this is initial value of the integral up to the time duration minus 1 divided by s. So, if you differentiate in the time domain, in the frequency domain you are multiplying by s. Similarly, if you multiply in the time domain, in the frequency domain you are differentiating. So, these two are dual role. Similarly, here also if you do the integration in the time domain, in the frequency domain you are dividing by s. By the same way, if you divide the signal x of t by t in the frequency domain, it will be something like integration. Okay, that's what we want to discuss in this lecture. Okay, and okay, so it corresponds to some integration in the frequency domain. Let us see what is that integration will be. Okay, integration in the frequency domain. So this is a property. This property, this is not very much useful. Okay, not important. But anyway, to complete the discussion, let us talk about this. So I think this is the 8th property. Let x of t and x of t divided by t be Laplace transformable. Okay, then s to infinity x of s times ds exist. Okay, so that means you are doing the integration in the s domain. Okay, what we mean by s to infinity is, suppose let us say this is your complex s plane, sigma and j omega. Okay, you put a line like this. This is your ROC. Then what we mean by s to okay. See, the range is from s to infinity. If you look at the integration, this is from s to infinity. So you take a value, and this values keep on increasing, but in this towards the real axis direction. Okay, s is increasing, or the limit is increasing in the real axis direction. That's what we mean by this in the limit. Okay, so We also assumed that both f of t and f of t, sorry, x of t and x of t by t both are Laplace transformable. Okay, so both, if it is Laplace transformable, then this has Laplace transform and this guy also has Laplace transform. That we will find out what it is, or we will derive it. Okay, then we take any point, let's say this point is S here, and then integrate this. Okay, integrate along this curve. Okay, this is my x of s over some contour starting from this point, and it goes up to infinity, so that the real part of s goes to infinity. That means when you take s equals infinity, the at least the real part of s is going to infinity. So one can possibly say that the point on the x-axis going towards the infinity, that is the end point. If you do that, then the theorem states that f of t by t has the Laplace transform integral of x of s ds. Maybe I can put some other variable. Already I have this one. I can put something like x of z times dz, some dummy variable, and s to infinity. Okay, since we are talking about s, to make it clear, okay, so you can we can put the dummy variable z here. Okay, where z is a complex variable. Instead of calling s, I put a z, that's all. And once you make the integration, it is a function of s. Okay, so after this integration, you substitute this s, substitute z equal to s and z equals infinity, then the result will be function of s. After all, z is a dummy variable, right? Now let us prove this. Here we assume that x of s is the Laplace transform of x of t. Now to avoid the confusion, we wrote x of z, some dummy variable. Okay, so instead of s, we are using the variable z. Okay, so instead of x of s, I am writing x of z, and integral of what is my x of z? X of z is equal to, see, actually what is the formula for x of s? X of s equal to integral of 0 to infinity, 0 minus to infinity, x of t e to the minus st dt. Now to avoid the confusion, what we are doing is, we are writing in terms of z. X of z is equal to 0 minus to infinity, x of t e to the minus zt and dt, that's it. Okay, now integrate this x of z from s to infinity, both side. That's what we want to find out now. So s to infinity, x of z times dz is equal to, this side also s to infinity, the whole thing x of z can substitute here, 0 minus to infinity, x of t e to the minus zt dt, then you multiply dz. Okay, here the limit is t equals 0 onwards, and here z equals s. Okay, here first integration is with respect to t, the second integration is with reference to z. So you can reverse the order of integration. So whatever functions are which are whatever functions are there which are independent of z, I will put them in the first position. Okay, so this I can, or this integral I can write as integral of t equals 0 minus to infinity x of t, then you integrate with respect to z first. So z equal to s to infinity e to the minus zt then dz, and then dt. Now you first finish this guy. Okay, so t is equal to 0 minus to infinity x of t, and this one if you integrate e to the minus zt and divided by minus z, and the limit is s to infinity. Okay, now and dt. The lower limit is s and upper limit is z. Now substitute the upper limit, then upper limit it becomes 0. Okay, because we are moving on the real axis, that's what we said here. Okay, so you are moving on the real axis, that is, after all, z is a complex number, let's say sigma plus j omega t. So e to the minus zt, it becomes e to the minus of sigma plus j omega times t. Now e to the minus sigma t times e to the minus j omega t. When this t equals s to infinity, if you put infinity here, e to the minus sigma times infinity, therefore this guy becomes 0, because you are moving in the real axis direction, right? Therefore the upper limit is 0 in this. 0 minus to infinity x of t, then 0 minus e to the minus st divided by minus z. I'm sorry. So you are doing the difference integration with respect to z, right? So therefore the denominator is not z, it is t, right? The integration is with reference to z, therefore the denominator is minus t. Fine. Minus t, that's it, and dt. So this is equal to t equals 0 minus to infinity, then minus times minus plus x of t by t e to the minus st and dt. Now if you look at this, don't you see, this is the definition of Laplace transform of x of t by t. Therefore this is equal to Laplace transform of x of t by t. The left hand side we started with the, if you look at this one, okay, so s to infinity x of z times dz. Okay, so division by t in the time domain corresponds to integration in the frequency domain. So integration in the frequency domain, just like integration in the time domain corresponds to division by s in the frequency domain. Okay, so as I mentioned at the beginning of this lecture, that this rule is not particularly useful to us in our context, in our application to systems and networks. So we will not further discuss about this. Okay, so we will just record this as a dual rule to the rule for integration in the time domain. So I will leave it at that point. So we will not discuss further in this. Okay, now let us move on to the next property. Now if you recall, in a solution of networks, transients and systems, network transients and systems, sometimes we may not be interested in finding out the entire function of time from its Laplace transform, okay, so which is available from the solution of a network. Suppose you have a network, let's say, then resistor, then again one resistor, then inductors, then one resistor, like this. You put a capacitor and inductor, then resistor, like this. So let's say this is my network now. In this network, you are closing the switch at t equals 0. Now I wanted to know what is the value of the circuit, or let's say the current or whatever it is, current or voltage. what is the network status at x equal at t equals 0 minus, or I would like to know what is the value at x at t, the moment you close the switch at that time what is x of 0 plus, and after long period you close the switch and allow the switch to be connected for t equals infinite amount of time, very long time, and then you wanted to know what is the value of final value, sorry, infinity. X of infinity. Okay, that means you allow t to go to infinity, then find what is the x of t value. The moment you close the switch, after immediately closing the switch, you wanted to know what is the x of t. Let us say this is my x of t, I am giving some voltage. The moment you close the switch, what is the value of x of t? That is t plus t equals 0 plus. So, you would like to know what is that, and you close the switch and wait for maybe a year or 2 years or 100 years, and then you want to know what is the value of x of t. When I say infinity means, it does not mean like infinite amount of duration, maybe some it is all like a relative terms. Okay. So, it can be 1 hour or 2 hours or like that, that will be sufficient. Okay, so in that case we may not be evaluate this x of t completely. So, how do you get x of t? By taking the inverse Laplace transform of x of s, then you have to do partial fraction expansion, we will see that. Okay. So, it is taking a lot of time. Now, people thought, is there any way to find out the this x of 0 plus and x of 0 minus, sorry, x of infinity without taking inverse Laplace transform, because in the time domain I wanted to know what is the value at t equals 0 plus, the moment you close the switch. Similarly, I wanted to know what is the value of the voltage when the switch is closed for a long time. Okay, you close the switch and apply certain amount of input like voltage or current. Okay, then you wanted to know what is the value of x of t after a long time, that is x of infinity. So, in that case you need to do find the solution. You first form the differential equations. From this you find the Laplace transform, then you will get x of s, then again you take a inverse Laplace transform, then you substitute t equals 0 plus or t goes to infinity. So, this is a lengthy process. So, instead of taking inverse Laplace transform, there is a shortcut. You can find out these two values, t equals 0 and t equals infinity, t tends to infinity, directly from the x of s. No need to take inverse Laplace transform. That is what we are going to talk about in the name of initial value theorem and final value theorem. Okay. So, we will be interested in finding out the initial value of x of t, that is x of 0 plus, and the final value of the x of t, that is x of infinity. Now, to find the initial value of x of t, then there is certain condition. So, what it says is, suppose x of s is given, we would like to know what is x of 0 plus. Okay. So, or what is the initial value of the derivative of x of 0 plus with respect to time at t equals 0 plus. So, without having to find the inverse Laplace transform from this ILT, no need. Okay. This can be done, this can be find out, either x of 0 plus or derivative of x of 0 plus can be found, okay, using a property of the Laplace transforms. So, which is known by the name of initial value theorem. Okay. So, this theorem is very, very useful. Now, let us state this initial value theorem formally. Okay. Now, under the specific constraints, that assume that x of t is equal to 0 for t less than 0. Why? Because I am closing the switch at t equals 0. Before that there is no input given to the network. Okay, and also this is my first condition. Second condition, x of t does not contain no impulse, or sorry, x of t contains no impulses, or it contains no higher order singularities. These are the conditions in order to apply the initial value theorem. Singularities. Okay, therefore, if you satisfy these three conditions, then one can directly calculate from the Laplace transform x of s the initial value x of 0 plus. What we mean by this x of 0 plus? It indicates that when t goes to infinity, okay, t approaches t approaches 0 plus from the positive values of t, then your x of t becomes x of 0 plus, and this is called the initial value theorem. So therefore, the initial value theorem is stated as x of 0 plus is equal to limit s goes to infinity s times x of s, and this is limit t goes to 0 plus time of x of t. That's it. This is your initial value theorem. That means you wanted to know just after closing the switch 0 plus. Okay, so we are not interested in x of 0 minus. Okay, not interested, we don't want. Just you close the switch, after that immediately what is the value? So that's what your initial value theorem says. Okay, now let us take some example for initial value theorem. Let's say x of s is equal to 0.9 s plus 1 divided by 2.1 s squared plus 5 s plus 6. Now through various techniques, okay, which we already know or which we will discuss later, you can find out x of t, okay, through using inverse Laplace transform. But suppose we are not interested in finding x of t, okay, we don't want x of t, we don't want the complete expression for, there are certain situations, okay, where we don't want the complete expression for x of t. X of t, we just wanted to know only what is x of 0 plus. We need to know only the value, we don't want the expression for x of t. In that case, what you do, this initial value theorem will be a boon for us. Okay, so the function of time, the x of t, and this time when it approaches the origin 0 plus from the positive side, then what is the value? So you can use the initial value theorem as I said. Therefore, x of 0 plus is equal to limit s goes to infinity, then s times f of s. So limit s goes to infinity, s approaches infinity, then s times the whole expression 0.9 s squared plus plus s, I am sorry, 0.9 s, so plus 1 whole divided by 2.1 s squared plus 5s plus 6. So limit s goes to infinity, then 0.9 s squared plus s whole divided by 2.1 s squared plus 5s plus 6. Okay, that means we can take only the ratio of the leading coefficient terms. So, who are leading coefficients here? This guy is a leading coefficient 0.9 s square and this 2.1 is the leading coefficient, because this 0.9 and this one and 5 and 6 become insignificant compared to with the first term, like s becomes large when s becomes large and larger, and this 5s and 6 becomes smaller compared to these two guys. Okay. So, therefore, you take the leading coefficient terms and ratios. So, this will be equal to 0.9 divided by 2.1, or if you want to do it mathematically, then what you do, limit s goes to infinity, then you take s square commonly, then 0.9 plus 1 over s divided by, here also you take s squared, then 2.1 plus 5 by s plus 6 by s squared. Okay, this s squared will get cancelled. Then this is, if you substitute s infinity, then 0.9 plus 1 over infinity divided by 2.1 plus 5 by infinity plus 6 by infinity. So, this all will become 0, then you will get 0.9 by 2.1. So, no need to do this kind of mathematics, simply by looking at here. So, these two are leading coefficients. Okay. This 0.9 is a leading coefficient, 2.1 is leading coefficient. Why is it called a leading coefficient? Because this term has s squared here. So, s squared will grow up much faster than the s term and then the constant. Therefore, you can avoid this s term and this 5s term and the 6 term. You can consider only these two. Straight away you can write the answer. Therefore, the initial value theorem will enable us to find out the initial value at t equals 0 plus of a function of time from its Laplace transform without having to go through the order of finding out f of t. Okay, without go through the ordeal of finding out f of t. Okay, ordeal of finding out x of t. No need to find out x of t. Okay, now let me take the second example. X of s is equal to s plus 1 divided by s plus 2. Now, what is x of 0 plus? Limit s goes to infinity, then s times x of s, then again s times s plus 1 divided by s plus 2, limit s goes to infinity. Now, limit as s goes to infinity, then s times f of s goes to infinity. Okay. Now, that violates the condition, because it is become s squared plus s divided by s plus 2. In the numerator I can take only s squared commonly outside, 1 plus 1 by s divided by s times 1 plus 2 by s. Then this you can cancel, again you have s terms 1 plus 1 by s divided by 1 plus 2 by s. Now, you substitute infinity, then infinity times 1 plus 0 divided by 1 plus 0. So, it becomes infinity. So, there is some problem. Okay. So, then what happens? This x of 0 plus is violated. That means this is actually an impulse. Okay. So, s plus 1 divided by s plus 2 can be written as s plus 2 minus 1 divided by s plus 2. So, this I can write as s plus 2 divided by s plus 2 minus 1 over s plus 2. And what is this? 1 minus s plus 2. If you take inverse Laplace transform, your x of t is going to be del of t minus e to the minus 2t times u of t. So, because of this delta function, the initial value theorem does not valid here. That is what we said when we started with the initial value theorem. Okay. X of t contains no impulses, and x of t is equal to 0 for t less than 0, and no higher order singularities. These are the three conditions we assumed for initial value theorem. Okay, but unfortunately in our thing it has an impulse. If you work on this for a given this example, if you work out to find x of t, then it contains del of t. So if it contains del of t, then you cannot apply initial value theorem, because initial value theorem talks about, after all, you want to find out x of 0 plus. At x of 0 plus you have an impulse, right? At t equals 0, the impulse is sitting like this. The impulse ranges from 0 minus to 0 plus. Therefore, at 0 minus or 0 plus, the strength is infinity. Therefore, the initial value becomes infinity in this guy. So you cannot find out the initial value theorem. You cannot apply the initial value theorem here if you have an impulse. So the impulse strength is infinity, but if you take the area of the impulse, yes, its area is going to be 1. That is well defined. But at exactly 0 plus, the magnitude is infinity. That is why here you got infinity, because the Laplace transform contains, or the signal contains, an impulse at the origin. So in that case you cannot find the initial value. Okay, so that is the reason for this example, for s plus 1 divided by s plus 2, you got the value of infinity. The justification is, if you take inverse Laplace transform, you found that there is an impulse del of t. We know that del of t is sitting in, if you enlarge, the del of t is sitting like this. This point is 0, and this point is 0 minus, and this point is 0 plus. At exactly 0 plus, what is the magnitude? The magnitude is infinity. So whenever you have an impulse which is sitting at the origin, then you cannot use the initial value theorem. That's it. So we will say that whenever a delta function exists at the origin, then we will not have the initial value theorem. So the initial value theorem is not applicable in such a situations, because it leads to infinity. After all, what is the initial value here? If you look at see, this is my, see, in the left hand side it is x of 0 plus. So the x of 0 plus becomes infinity. So it is not useful unless you talk about infinity in magnitude. Now consider the dual rule of this, which gives the final value theorem. Okay, final value of a function of time without having to find out the inverse Laplace transformation. I think this is a 10th property. Where is initial value theorem? Yeah, this one is 9th property. So final value theorem. Again, the final value theorem also very simple. Let me state the theorem first here. The final value theorem says that final value means what? When t goes to infinity, finally, okay, where you close the switch and wait for a sufficient amount of time, quite a long time, then you wanted to know what is the value of x of t. That's what we mean by final value theorem. Therefore, limit t goes to infinity x of t. So this we wrote as x of infinity. Okay, this x of infinity is equal to limit s goes to 0, s times x of s. Okay, so this is the final value theorem statement. Now we have seen in the initial value theorem that the behavior of s times f of s at s equals infinity essentially governs the value of x of t at t equals 0. As a dual to this, the behavior of x of s at s equal to 0 will eventually dictate the value of x of t when t goes to infinity. And this is given by the statement of what is called this final value theorem. Okay, there are certain conditions for final value theorem before you apply this, like x of t and x dash of t both are Laplace transformable. That is the first condition. Okay, first condition. And the second condition is s times x of s has no poles. When I take the example, then that time this will be very clear, these statements. X of t has no poles on the j omega axis. Okay, similarly s times x of s has no poles on the right half s plane. So these are the three conditions that one should make sure before you apply the final value theorem. Sigma j omega. So this is my ROC, like this at least. So s times x of s has no poles in the shaded area or hatched area. So if you have a pole on the imaginary axis or in the right half plane, then the final value theorem is no longer valid. Okay, we will see why it is no longer valid. Okay, so s times x, not x of s. Okay, note the condition very carefully. I did not say x of s should not have any poles in the right hand side. S times x of s must not have any poles in the right hand side or in the imaginary axis. Okay, now let us take an example. X of s is equal to 4 divided by s times s plus 1. Now we would like to know whether we can find the f of infinity without having our finding out f of without having to find out x of t. See, if you take inverse Laplace transform, then you will get x of t, and then you substitute limit t goes to infinity, then you will get a x of infinity. But don't do this. Okay, it is a lengthy process. Directly you can find out. That is the beauty of your final value theorem. So your final value theorem says limit t goes to infinity x of t is equal to limit s goes to 0 s times x of s. Now if you multiply s times x of s, what will happen? S times 4 divided by s times s plus 1. Then s and s will get cancelled. So you will get 4 divided by s plus 1. So what is the pole location? At minus 1. No problem. So this s times x of s does not have any pole on the right hand side as well as on the imaginary axis. This is my j omega and this is sigma. So therefore those three conditions are satisfied. So limit s goes to 0, 4 divided by what is that? S plus 1. Now if s goes to 0, then 4 divided by 1, which is 4. So this is the final value theorem of the given function. Even if you want, you can take the inverse Laplace transform and then you substitute t goes to infinity, then you can prove it. So the final value of the time function is 4 units. Okay, so we did not have to really find x of t. So this tells us that the advantage of this theorem, without having to find out the particular analytical expression for x of t from x of s, which sometimes can be complicated. It will be a lengthy calculation, lengthy derivation. So we can straight away find out the final value without having to go through this intermediate steps of finding x of t. Let me take one more example. Let us say x of s is equal to 4s plus 91 divided by 123 s, let us say s squared plus 63 s. Okay, now limit t goes to infinity, x of t is equal to limit s goes to infinity, s times x of s. Now you multiply s in the numerator, then it becomes s times 4s plus 91. The denominator I can take s commonly outside, 12. If you take s, then 123s plus 63. This s and that s will get cancelled. Now limit s goes to 0. Limit s goes to 0, 4s plus 91 divided by 123 s plus 63. Now before you substitute the limit, make sure that there is no pole in the right half of the s plane. What is the pole of, what is the numerator will give you the zeros. So 4s plus 91 is equal to 0, therefore s1 is minus 91 by 4. In the denominator, what is the pole? 123. 123 s plus 63 equals 0, therefore 123 s equals minus 63, s equals minus 63 by 123. So both are lying in the left half of the s plane. Minus 63 by 123, let us say this is my roughly minus 0.5, minus 63 by 123, then this is the pole location, and 91 by 4, it's roughly some 18 or 20, so it will be somewhere else. So this is minus 91 by 4, minus 63 by 123. Pole is located by cross symbol and 0 is marked by small circle in the complex plane, complex s plane, and this is your j omega axis, and this one is what? Real axis sigma. Now you can happily apply the final value theorem, like s goes to 0, therefore 0 plus 91 divided by 0 plus 63. So the final value is 91 by 63. Now another example, let me consider s divided by s square plus 1. Now what is this? Of course, if you look at this one is nothing but cos of t times u of t. If you look at a cos omega naught t u of t, what is its Laplace transform? S divided by s squared plus omega naught squared. Now omega naught squared is equal to 1. That is why I wrote cos t times u of t. So the final value theorem, if you like to apply for this, you must multiply this by s first. So this is s squared divided by s squared plus 1. So you will get a 0 by 1, which is 0. Okay. If you apply the limit s goes to 0, then you will get this answer. But then what is the final value of cos t? You have a cos function like this, keep on oscillates. Now you wait up to infinity, you keep on go and wait up to t equals infinity. Then also this guy will not settle down, it is keep on oscillating. So we can't say what it will be when t becomes infinity. It can be 0, it can be plus 1, or it can be minus 1, we don't know. So if you take the average of that, it may be 0. Okay. So the maximum value will be plus 1 and the minimum value will be minus 1. If you take of that, then average value will be 0, but you cannot exactly say what is the final value. Okay. But then the point to observe is the important point to observe in the final value theorem is that s divided by s square plus 1 will not satisfy the statement of the theorem. What is the statement of the theorem? If you look at it should not contain any poles on the right half of the S plane, or it should not have any poles on the j omega axis. But here if you look at S squared equal, in the numerator you have S squared after multiplying by S, in the denominator you have S squared plus 1. So the zeros you have two zeros, multiple zeros, 0 comma 0. In the denominator you have S squared plus 1 is equal to 0, that means S is equal to plus or minus j. So you have two poles, one pole is here plus j and another pole is minus j. But as per the final value theorem statement, S times x of s must not have any poles on j omega axis. Therefore, the final value theorem fails here. You cannot apply the final value theorem. Two poles are located on the imaginary axis. So S times x of s is equal to S squared divided by S squared plus 1. Will have poles at plus or minus j. Therefore, the final value theorem does not apply. So the final value theorem does not apply in this case, and therefore whatever limit you get may or may not be true. Okay, sometimes this value, no, you cannot say the value is 0 because this is what we got. Sometimes no, if you apply, then you may get some other value. Therefore, we cannot use this, okay, whenever S times x of s has poles either in the j omega axis or in the right half plane. The first point what you have to do is find the location of the poles, whether the poles are located in the right half of the S plane or on the j omega axis. Then you apply the final value theorem, otherwise the final value theorem will not be valid. By the same reason you can say for sin omega t also, sin t also you can say. Suppose let us say x of s is equal to 1 divided by s square plus 1, then this is sin t. For this value also you cannot apply final value theorem FVT. Okay. So in this lecture we discussed division by t and the other two properties, initial value theorem and final value theorem. So let me stop at this point. In the next lecture we will talk about convolution in time domain and so on. Thank you very much.